Okay, so thank you very much. So my name is Luca Gallo. Today I will present my thesis work that is titled Coupled Dynamical Systems in Presence of High-Order Interactions. This is a work I have conducted under the supervision of my three supervisors, Professors Vito Latora and Mattia Frasca from the University of Catania, and Professor Timoteo Carletti from the University of Namur in Belgium. Okay, so this is the table of contents of my presentation. I will start by introducing you the context and the motivation for this work, which is about high-order interactions in complex systems. And so I will then talk about high-order networks, so the mathematical structure with which we represent complex systems with high-order interaction. I will then move to dynamical systems, talking to you about coupled systems with many groups, many body interactions. And in particular, I will focus on two applications, on two phenomena that are synchronization and Turing pattern formation. And finally, I will conclude summarizing the work. So in the last 2 or 3 decades, many natural, social, and artificial complex systems have been modeled using a great tool, which is complex networks. Sorry for that. I booked the room, so
yes.
Yeah, sorry. Can you? Is it okay?
Yes, I'm here to take away my.
Yeah, sorry. I'm gonna discuss with. Okay. Yeah, sorry for interrupting, but I have booked a room in my university, which is shared. So yeah, it was an overlap for booking. Sorry. Okay, I was saying that networks are been a great reference tool for modeling complex systems, and in many cases, a node can be modeled as a dynamical system, so that the overall dynamics of a system is shaped by the interplay between the structure of the complex network and the dynamics of the isolated node, and by the form of the interaction, so by how the units interact together. However, though they are great, networks have some limitations, and well, actually they have many, but I will focus on a particular aspect of networks. So the fact that they can only describe pairwise interaction, so interaction between couple of units. And this is because recent evidence has shown that different systems are actually characterized by group interactions. For instance, we as humans interact in group, and so a network description is not enough to describe the variety of interaction in human societies. As another example, the brain is inherently higher order in the sense that for a neuron to be active, it has to interact with multiple neurons at the same time. But let me go deep in what high-order interactions in the context of complex systems are. And let me focus on a particular example coming from ecology. So you have two species, a forb and a grass, that compete for nutrients. And how do they compete? They compete by inhibiting the growth of the other. So let me focus here on the action that a forb has on a grass, in the sense that it inhibits the grass. So if we consider the system like this, we can describe it with networks, and we can also do it if we add a third species, which is a shrub, that somehow has an impact on the grass, an indirect impact on the grass by having an active impact on the forb. What I mean is that the shrub inhibits the forb, and so as the forb is inhibited, the action or the inhibition of the forb to the grass is at the same time inhibited. This is somehow high order, but this is not what I will mean for high order through this presentation. Rather, this is what I will mean for high order: a situation in which the presence of the shrub does not affect indirectly the grass, but it affects directly the action of the forb to the grass. And this direct action on the action of the forb cannot be modeled using complex networks. But we will see that we will need more complex structures to describe an interaction like this one. So this to make clear what I mean for high order interaction. Okay, so in the thesis, I have focused on two phenomena, the first one being synchronization. Synchronization is an emergent phenomenon which is ubiquitous in our words. We see synchronization of neural activities, which is associated to epileptic seizures and other phenomena like this one. But we also see synchronization in biology in a more beautiful way when fireflies synchronize their flashes. But we also see synchronization in human ensembles, in an orchestra playing, a group of ballerina dancing, also in pedestrian walking. So as you see, synchronization is definitely everywhere. And because of this ubiquity, the role of higher-order interactions have been greatly studied in the context of synchronization. And for instance, there are some results showing how high-order interaction can modify the evolution towards synchronization. In particular, here I would like to show you an example coming from a paper by Scardel and Arenas, which shows that higher order interaction can dramatically change the collective behavior of a system. So in this paper, the authors focus on the Kuramoto model, which is a paradigmatic example of phase oscillators. And this Kuramoto model is well known to have a continuous transition. What do I mean? I mean that the system, as we increase the strength of the coupling, of the strength of the interaction, the system goes from a situation in which it is incoherent and continuously moves toward coherence, towards synchronization. And this happens for pairwise interactions only. But when we add higher order interactions, this transition becomes abrupt. And so we start from an incoherent state, and explosively, in a very sharp wave, we go towards synchronization. And this is due to higher order interactions. But despite these great and interesting results, most of the research so far have focused on phase oscillators, or on the Kuramoto model, as I was saying, and less attention has been given to nonlinear chaotic oscillators. Furthermore, most of the results so far have been restricted to numerical simulation, and when they provide an analytical solution, they do it only for simplified cases. And what we would like is a more general theory for synchronization. The second phenomenon we focus on is pattern formation. And patterns, like synchronization, is everywhere in nature. We see patterns in how animals divide their territory. We see a variety of patterns on the animal themselves. We see them on the shell and on the fur of animals. But we also see pattern formation in how amoebas aggregate. So again, because of this ubiquity, pattern formation has been already studied in the context of many body interactions. I would say less than synchronization, but still. So, for instance, in this paper, the authors showed that the presence of high order interaction can change the behavior of the system. So, for instance, if you consider a case in which there are pairwise interactions only, which is shown in the figure on the left, you see that no patterns can form. So you see a very homogeneous space. But when we add higher order interactions, then patterns can form, then an heterogeneous solution arises. So in a nutshell, higher order interaction change the collective behavior of a system. But despite this work, the current framework remains limited to the case of linear coupling functions, and we would like to have a more general theory, general extension of Turing instability theory for high-order networks, which remains an open problem. So to wrap up, the motivation for this thesis is that we need to develop a general theory to study coupled dynamical systems in presence of higher-order interactions. So to do that, we rely on high-order networks. Imagine you have a dataset like this one, a dataset consisting of pairwise interactions, the one in white, among units 1 and 2, and 2 and 3, and so on, but also many body interactions. So here we have 2 3-bodies interaction and 1 4-body interaction. If you want to use a network description to represent this data set, you will come up with something like this. And as you can see, you cannot clearly understand where are the higher order interactions that are here. And why that? Because, as I was saying, networks are limited. They are only able to describe pairwise interaction. So there is no way of naturally representing this high order interaction with networks. So we need to rely on more complex structures like simplicial complexes and hypergraphs, and where you can see that they naturally capture many body interactions. So throughout this presentation, I will focus on hypergraphs because they are the most general structure, as simplicial complexes are, after all, a particular case of hypergraphs. But the mathematical framework I will present to you is general enough to describe both structures. Okay, so how we represent high-order networks? When we represent networks, we usually rely on adjacency matrices. The adjacency matrix is a matrix n times n, where n is the number of nodes, whose entries ij are either 1 or 0. They are 1 if there is a link ij, so a link between the units I and j, so ij is part of the edge set, and is 0 otherwise. And in the case of undirected structures, so of structures representing reciprocal interactions, we have that if an element ij is equal to 1, then the element ji of the adjacency matrix is also equal to 1, meaning that the adjacency matrix is symmetric. Okay, so when we have a high-order interaction, we have different orders of interactions. And so a single adjacency matrix is not enough. We need to rely on a set of adjacency tensors. So when A1 represents the adjacency matrix, the standard one, A2 represents the three bodies interaction. A2 is a tensor of 3 indices. A3 represents the 4 bodies interaction, and so on. But the idea is the same. The idea is to have a tensor whose entries are binary, either 1 or 0. It's 1 if there is an interaction among m plus 1 nodes, and so if this set is part of the hyperedge set H, it is 0 otherwise. And similarly to what we have done for networks, we also have a symmetry property for undirected structures, so that if the element corresponding to indices I1 up to im plus 1 is equal to 1, then all the elements associated to the permutation, to all the possible permutations of these indices are also equal to 1. Okay, let me point out here that this is valid for undirected structures only. So when I will talk about directed structures, which instead represent non-reciprocal interactions, you see that this relationship is slightly different. But at this point, I won't go in further detail, just wanted to point it out. Okay, given the adjacency tensors, we can now generalize the concept of the degree. The degree is basically the number of links adjacent to one node. But here we have more complex structures, so we need to have a set of degrees, again, one for each order of interaction. On the right, you see the definition of the generalized node degree, and on the left, you see an example. So if I focus on node I, you see that the number of links adjacent to node I is 2, so K1, the standard degree, is equal to 2. As I does not participate in any three-body interaction, we have that K2 is equal to 0, and as it participates in one four-body interaction, K3 is equal to 1. But for hypergraphs, we can do even more and define a generalized link degree, so which is the number of interactions of order m in which two nodes I and j participate. Okay, so again, by looking at the figure on the left, we see that K1 ij is equal to 1, as there is a link between I and j. K2 is coherently equal to 0, and K3 is equal to 1, as both nodes I and j participates in the four-body interactions. Given the degrees, we can now generalize the Laplacian matrix. The Laplacian matrix is quite important in dynamical systems on networks, as it is associated to many processes like diffusion, random walk, and as we will see, synchronization and Turing pattern formation. For the network, we have this definition of the entries of the Laplacian matrix. On the main diagonal, we have the degrees of the node. On the off-diagonal terms, we have instead the adjacency matrix. And for hypergraphs, we have again a set of Laplacian matrices, and for each order, we have on the main diagonal the corresponding generalized node degree, and on the off-diagonal terms, we have the corresponding link degree. Okay, this concludes the part regarding the representation of high-order networks. Let me now go to dynamical systems. So when we study coupled systems in networks, we usually study an equation like this one, in which the state of a unit I is determined by, is described by a vector x of I, whose dynamics is determined by a function f, which determines the dynamics of the isolated unit. and by a coupling term, which instead encodes the contribution of the interactions. And this coupling term has some ingredients. We have a coupling strength sigma 1. We have the contribution of the structure of the interaction through the adjacency matrix A1. And we also have the coupling functions H, which determines the form of the interaction. And as you will see, this coupling term is diffusive, so we have a difference between two functions. This is the system that we have studied instead. So this system in which higher order interactions are presented. This is the first contribution of the thesis. And as you can see, this equation is more complex because now we are taking into account multiple ways in which units can interact. But before telling you how we study synchronization and Turing pattern formation on this equation, let me take a step back and focus on coupled systems on networks, because they're easier to explain, and as we will see, they are not so different from high-order networks. So here, I take the same equation. I have dropped some parentheses to make the notation less cumbersome, but there it is. So when we study synchronization and Turing pattern formation, we study a solution X bar, which is an homogeneous solution of the isolated system. So what are synchronization and Turing pattern formation? In the case of synchronization, we have multiple oscillators that we want to converge to the same reference solution. Indeed, this is synchronization. It's the fact that we start from different conditions, or from oscillators having different conditions, and after a transient, they all follow the same trajectory. So in the case of synchronization, we want the units to converge to a synchronous trajectory, so to a trajectory x bar equal xs, which is dependent on time. Okay, so we want this convergence. For Turing pattern formation, somehow we want exactly the opposite. Indeed, if we start from an homogeneous solution, which is not a trajectory in this case, but it is a fixed point, it is a stable solution. If we perturb the system around the solution, we want it not to come back to this homogeneous state, but we want it to go to an heterogeneous one, because this heterogeneity is what patterns are. So in the case of pattern formation, we want the units to diverge from an homogeneous fixed point, so from a solution, from a reference solution x bar equal x star, where the two notations define the fact that the first, for synchronization, we are studying a trajectory, the synchronization manifold. For Turing pattern formation, we are studying instead a fixed point. But the idea is the same. The idea is to study the stability of a reference solution which is homogeneous. And how we do that? We do it by linearizing the system around the reference solution. And here you can clearly see the role of the Laplacian matrix. Okay, so now the system is linearized, but yet is still coupled. Okay, and we would like to have a decoupled system. Instead of having one single system of n coupled equations, we'd like to have n decoupled equations. And to do that, we can project the perturbations delta xi onto the eigenbasis of the Laplacian matrix. So to have n equations, each one of them depending on one eigenvalue of the Laplacian matrix. But as you see, now we have n decoupled equations that have all the same form. So instead of studying all of them, we can actually study one single equation, the master stability equation that you see on top, that depends on a single parameter alpha. So we study the problem of synchronization and Turing pattern formation in terms of a master stability function. And this holds, as I was saying, for both synchronization and Turing pattern formation. In the case of synchronization, we want this master stability function, which is the maximum Lyapunov exponent, to be negative, because this means that the perturbation decreases in time. So we go back to the synchronous state. While for Turing patterns, we want the dispersion relation, because in this case it's called the dispersion relation, to be positive, because this means that the perturbation instead grows in time. So we go away from the homogeneous fixed point and we go instead towards an heterogeneous one. So these two phenomena that in principle are completely different can be studied using the same mathematical framework. And this is the idea of the thesis. Okay, going back to the most general system that we have studied, here we can perform the same analytical treatment and linearize the system. And when we do that, we go to an equation which is like that. Now, this seems a little bit different from the one you've seen before, because this is written in a more compact form, because this delta x vector encodes and contains all the perturbation for all the possible units. But the main aspect here is that you see there are m Laplacian matrices, L1 to up to Lm, or each of them encoding one order of interaction. So, okay, at this point, we would like to decouple the system again, but in general, this is not possible. And this is not possible because, in general, the Laplacian matrices do not commute. So it is not possible to find an eigenbasis that diagonalize all of them at the same time. So it seems like we are stuck, but actually, there are some special cases in which we can derive a single master stability equation, the first one being the case of natural coupling. So the natural coupling is an hypothesis on the coupling function that you see on the left. And the idea is the following. Imagine you have a node in state X interacting through the function H2 with two nodes in state Y, in the same state Y. The idea of the natural coupling is to say that this node in state X interacts with the two nodes in the same way as it would interact with a single node through the function H1 in the state Y. So there is some idea of equivalence between among the orders of interactions. And under this natural coupling hypothesis, we can define an effective Laplacian matrix that now encodes all orders of interactions. And with that, we can again write a single master stability equation, where this time the parameter alpha is not related to the eigenvalues of the standard Laplacian matrix L1, but is related to the eigenvalues of L, which again encodes all orders of interactions. The second special case is maybe the most trivial one. It is the case when the Laplacian matrices actually commute. And there are some structures, and I will show you one next, where this happens. And when Laplacian matrices commute, we can write a master stability equation, which does not depend anymore on a single parameter, but it depends on a set of m parameters, one for each order of interactions. Okay, so this concludes the part, so the presentation of the mathematical framework I've introduced with the thesis. Now we'll focus on the applications. And first of all, I will start with synchronization. So in the thesis, you find that I have studied different chaotic oscillators, but here in the presentation for brevity, I will focus on the Rosler oscillator only. The equation of the isolated system is written on the left, and on the right you see a representation of its attractor. First of all, we evaluated the master stability function for a system of coupled Rosler oscillators with different coupling schemes. All of them consist of 2 and 3 bodies interaction that are nonlinear, diffusive-like, and that satisfy the natural coupling hypothesis. So these are the results for 9 configurations considered. I won't go in detail here. I just want to show you that there are a variety of behaviors. So, for example, we have a case in which the master stability function is always positive, meaning that for every value of alpha, we cannot synchronize the system as the perturbation always grew. We have here another example in which after a certain threshold value of alpha, the master stability function is negative, meaning that after this threshold value, we can synchronize the system. So if the coupling is strong enough, basically. But the most interesting one is maybe this letter, in which you see that the master stability function is negative for a given interval of values of alpha, meaning that the spectrum of the effective Laplacian matrix has to fall entirely within this interval, so to have synchronization. And now I will focus a little bit more on this last example. The equation for this last example are written here. You see that the Rosler oscillator is coupled. The Rosler oscillators are coupled through the X component. You see that there are 2 and 3 bodies interaction in the form I told you about. So we studied a bit more in detail this system. And in particular, we studied whether the master stability function was able to predict the synchronization behavior of a system on a real-world structure. And in particular, we considered the Zachary-Carothers club network and extended it to an higher order representation. And basically what we did was to take each triple of nodes and add the possibility of for each triple to interact also through a 3-body interaction. So basically in this case we have a simplicial complex. Just wanted to point it out. And we did it for different values of sigma 1 and sigma 2. So we ran the numerical simulation for different values of the coupling strength and monitor the state of the system, the synchronization state, through a synchronization error E. And these results are shown in the heat map on the right. The figure on the right also shows the theoretical prediction, so the master stability function. In particular, we show the values of sigma 1 and sigma 2 for which the master stability function is 0. So within this area, we have that the master stability function is negative. This means that the eigenvalues, again, I'd like to stress it, the eigenvalues of the effective Laplacian matrix, which depends on sigma 1 and sigma 2, fall within the interval where the master stability function is negative. And as you can see, this area is able to well predict where the synchronization error goes to 0. So it is able to well predict when the systems synchronize. Okay, this concludes the part regarding reciprocal interaction. I will now focus on non-reciprocal interactions. Why that? Because there are many systems in which the interactions are definitely, there is definitely a privileged direction in the interaction. For instance, again, in group interaction in humans, we often see asymmetries. Imagine the relationship between a mentor and his or her mentees, or the relationship between a group and its leader. Of course, the interaction is not symmetric. Again, we have the same example from ecology, in which we have 3 species, one affecting another, and a third species acting as a mediator, but this action of one species to another is again directed. And a third example in which we have a definitely asymmetrical and many body processes, that of cell pathways, in which you see these processes contain many proteins that are in a directed way. So these are just a few examples, but how do we represent non-reciprocal interaction? So how can we extend the representation I told you about? So imagine you have 3 units, I, J, and K, interacting in a reciprocal way. What does this mean? It means that each unit feels the presence of the others. So it means that unit I is influenced by unit J and K, unit J is influenced by unit I and K, unit K is influenced by units I and J. Okay, so a reciprocal interaction among 3 units can be seen as the sum of 3 non-reciprocal interactions, in each of which there is one node as a target and the other node as the source. And this reflects also on the adjacency tensor A2. So for the reciprocal interaction, we have 6 elements associated to the permutations of indices I, J, and K that are equal to 1, and they all encode the same reciprocal interaction. But if we can group these 6 elements in 3 groups of 2, and in each group represent one non-reciprocal interaction. So for instance, the elements IJK and IKJ represent the interaction directed towards node I. And if you look at the first 2 equations, so the one for the reciprocal interaction and the non-reciprocal targeting I, you see how the symmetry property I was telling you about changes in the context of directed networks. Because for a reciprocal interaction, you can permute every index, you can flip every index. But for directed structures, if you change, for instance, index I with index J, you change the interaction. So it's not symmetrical anymore, because changing I and J, it means to change the target of the interaction. So this is how the tensor symmetry property change in presence of Highorder, in presence of directionality. And so given this new property, we can again we can extend the definition of the generalized degree to generalize in degrees, and we can do it for the node. And now K in I is the number of interactions targeting node I. And we can also extend the definition of the link degree to the link in degree. And here we have that K in Ij is the number of interactions targeting node I and having J as a further source node. And here notice that Kij is different from Kji because of the same thing I told you before, because the first one represents the number of interaction pointing towards E and having J as a further node, and the other one is the number of interaction pointing towards J and having I as a node among the source nodes. So they are not the same in general. And as maybe you remember that these terms are the off-diagonal terms of the Laplacian matrices. And so as these 2 terms are now different, the Laplacian matrices are in general non-symmetric. And because of that, the master stability equation is not anymore defined by a single real parameter, but is now defined by a single complex parameter. Because in general, the eigenvalues of the non-symmetric Laplacian matrices are complex. So this is how the theoretical framework we have developed changes in presence of directionality. So again, we come back to the Rosler oscillator and to the system of coupled Rosler oscillators on the X component. The equation looks the same, but here remember now that A1 and A2 are in principle are different from those I showed you before. And so to study the system, we set up the following numerical analysis. We define a reciprocity parameter P, which goes from 0 to 1. And when P is equal to 0, we basically select one out of the three non-reciprocal three-body interactions. So basically, P is the weight of the other two directions, and we tune this reciprocity parameter up to P equal 1. When P is equal to 1, all the interactions have the same weight, and basically we recover a undirected structure where all interactions are reciprocal. So we have basically defined a parameter for which we can tune the directionality within the system. Okay, in particular, we studied this network in which we start from a ring, from a node disposed on a ring, in which we add three bodies interaction, the directionality of which can be tuned using this parameter P. And we studied how the eigenvalues are in comparison within the stability region defined by the master stability function, whether they are all within or somehow some of them is outside of the stability region, with different values of sigma 1, so with different values of the coupling strength of the pairwise interaction. And this is the result. Here in white, you see the values of sigma 1 and P for which all the eigenvalues are within the stability region, and in blue, you see the opposite case. So you see that for there is an interval of values of sigma 1 for which varying P does not change the behavior of the system. But instead, there are also other values of sigma for which we see phase transition. For instance, here, we see the synchronization as we increase P. And this comes because we increase the reciprocity parameter, and one eigenvalue or more eigenvalues which starts within the stability region, which is the white area in both panels. So notice that panel B is just a zoom of the area close to the origin. So I was saying there are some eigenvalues that start within the stability region, and as we increase P, they go outside of it, destabilizing the system. But we also have the opposite scenario. We also have the other phase transition in which we start non-synchronized, and as we increase the value of P, the system synchronizes, meaning that the eigenvalues that starts outside of the stability region after a certain value of P go within it. And so, long story short, it is quite important to look at directionality, because directionality can dramatically change the behavior, the synchronization behavior of the system, either inducing its synchronization or destabilizing the synchronous state. So this concludes the application of synchronization. Now we'll focus on Turing pattern formation. For Turing pattern formation, I focused on the Bruce-Lator model. The Bruce-Lator model is well known for those who are studying Turing pattern formation. It is a reference model for it. And we started a system of coupled Bruce-Lators with, again, 2 and 3 bodies interaction. So the novel contribution is, again, the part highlighted in orange, so which is the 3-body interaction term. Okay, if you look at the coupling function, it might look like they satisfy the natural coupling hypothesis because they have the same order of the polynomial, but actually they do not, as du1 and du2 and respectively dv1 and dv2 are in general different. And as they are different, these coupling functions then do not satisfy this natural coupling hypothesis. And why that? Because we also wanted to study the other case in which instead the Laplacian matrices associated to the structure commute. And the structure I chose to present here is the 2 lattice. So the 2 lattice is a high-order generalization of a triangular lattice. Triangular lattice is a lattice where all nodes interact with 6 neighbors. And if we add the possibility for each triple of nodes to interact in 3, then we have the so-called 2 lattice. And in this case, the corresponding Laplacian matrices L2 and L1 are basically the same matrix up to a factor 2. So they commute in this case. So So we can define a mass stability equation and evaluate the dispersion relation for this system. Okay, so these are the results. So if we take pairwise interaction only, so we can set the system in a configuration of values of sigma 1, sigma 2, and the coupling coefficients, so that with pairwise interactions only, we are not able to induce pattern formation. So the dispersion relation is always below 0. But in this configuration, when we had Highorder interaction, you see that the dispersion relation changes due to the presence of Highorder interaction, so that there are values of alpha for which the dispersion relation is actually positive. And this means that in theory, we can witness the emergence of patterns. And this is confirmed by numerical analysis. You see here, you have U star, which is the reference solution, the homogeneous solution. And in this case, the oscillators go toward an heterogeneous fixed point. So they do not converge towards U star, meaning that here our theory is able to predict the formation of patterns. But we have also the opposite scenario, in which if we set the system in a way in which the pairwise interaction only can allow the presence of patterns, and we can add high-order interactions, and in this case, the dispersion relation goes below 0 entirely. This means that high-order interaction in this case can suppress the formation of patterns. And this is again confirmed by the numerical simulation, where you see that all oscillators converge towards U star. So again, in a nutshell, high order interactions, as this confirms previous results, but in a more general framework, high order interactions can greatly change how patterns form. They can induce their formation, or in another way, they can suppress it. So, in conclusion, with this thesis, I've described how to represent systems characterized by high-order interaction using a graph theoretical approach and the corresponding tensor representation. I have introduced a new formalism that allows me to, and allows us in general to study coupled dynamics in a general framework, so coupled systems in presence of high-order interactions. And in particular, with this framework, I have derived the necessary condition for synchronization in two scenarios. The first one in a scenario where the high-order interactions were reciprocal, and in another one in which they were non-reciprocal. And finally, this framework allowed to extend Turing's instability theory to the case of high-order networks. So, okay, this concludes the presentation. Here you see my list of publications. The first 3 works are related to the results I've shown you today. The other 3 are works that I have carried out during the PhD, but they didn't find space because of the topic on in the thesis. They are about epidemics, COVID-19, and also applications of complex networks. And before I finish, I'd like to acknowledge all the great people that you see on this slide, and also all the fantastic people that you do not see on this slide, as the slide is maybe too little to contain them all. And I'd like to thank you all, because you definitely made this possible. So with this, I conclude. Thank you for your attention, and I'm open for questions.